Dear students, today we are going to see the representation of numbers in computer. Actually, we know that the numbers are converted into binary and the binary numbers are stored in the computer. But that itself is done either in fixed or floating point format. So most of the computers are using the floating point representation of binary numbers. So we will see the steps how the numbers are converted into floating point, what is a floating point number, what is scientific notation, all these things we will cover in this video. So there are two types of storage of real numbers, that is one by fixed point and another is floating point representation. Fixed point means the numbers are fixed, okay. So two types are there, unsigned fixed point as well as signed fixed point. Where unsigned we have integer and fraction, but in signed fixed point we are having a sign as the first bit, then there is integer as well as fraction. So we will see a certain example. Normally these numbers are stored either in sign magnitude form, already we have covered, or in 1's complement or 2's complement form. So assume that we are having a number, a decimal number, it's given as minus 43.625. How we have to represent this using the fixed point notation or fixed point representation? So you simply convert the number into binary, and since this is a negative number, the sign bit is 1, then the integer part is the part before the decimal point, that is 43. Corresponding integer, you have to write the binary of that 43. Here we have 15 bits reserved for that. So the remaining bits you have to fill with zeros, so that there will not be any change in value. Similarly, the fractional values, here it is 0.625, the corresponding decimal is 1010, and the remaining portions you have to fill with zeros. So the features are that the fixed point representation is fast and inexpensive, but it is having a major disadvantage, that is it has a limited range of numbers, as well as there are chances of errors due to overflow. So we are going for the floating point. The floating point numbers are actually the numbers that is represented in scientific notation. So what is a scientific notation? A big number or a very small number you can convert into a particular form, that is which consists of the number and there is a base and there is an exponent. Here you can see the number, a very huge number, that is converted into scientific notation with a single digit on the left side of the decimal, that is 7.452 into 10 raised to 21. It is in the form m into b raised to e, where m is the Mandisa. Here it is 7.452, then base is 10 and the exponent is 21. You can see another example, it's a negative number as well as it's a very small value. You can see the same number can be represented conveniently into scientific notation as minus 2.32 into 10 raised to minus 14. So keep in mind that the floating point numbers are nothing but the scientific notation of or scientific representation of the numbers, whether it is positive or negative or very huge number, very small number. Irrespective of this, we can convert the number into floating point representation, and it will extend the range of the numbers. Very huge number as well as very small number can be represented like this. We will see a certain example. Okay. So three parts are there for a floating point. We are having a sign, the first bit corresponds to the sign bit, then there is a Mandisa, that is called again significand, and there is an exponent. Okay. So the form is m into b raised to e, where m is the Mandisa, b is the base and e is the exponent. A simple example, we have given 8 bit reserved for storing a floating point number. The first bit is for sign, then there is 4 bit for exponent, and there is 3 bit for Mandisa. See another example, a huge number we want to convert into the floating point. Okay, it's simple, 1.23 to 10 raised to 10, simply the scientific notation. Okay, then there is again another number which is given in binary. So here you have to take care, the base is 2, so the number will be like this, 1.01001 into 2 raised to 23. It is not 10 raised to 23 because the number is a binary, the base is 2. Again another number, it's a very small negative number. Here the number is again 2 raised to minus 24, minus 1.01 into 2 raised to minus 24. In floating point representation, very popular standards are there. One is IEEE 754, that is having single precision as well as double precision. So the numbers, even the numbers are represented in binary in computer. Actually that follows either a IEEE standard of single precision or double precision. We will see one by one. So 32-bit single precision number, first we will be discussing on that. Okay, as we have mentioned, 3 parts are there. One is the sign, then exponent and mantissa. So here 32-bit single precision IEEE 754 standard, the sign bit is the first bit. Okay, that starts from the left, that is the single bit is used for representing the sign. Positive, if the number is positive, it's 0, and it is negative, the sign is, you have to put a 1 there for negative numbers. Then 3 bits are reserved for exponent. Okay, sorry, 8 bits are reserved for exponent, and 23 bits, the remaining 23 bits are reserved for the mantissa or the fraction. Okay, this is the general format for a IEEE 754. Total 32 bit, 1 bit for sign, 8 bit for exponent and 23 bit for fraction. Okay, so we will see 1 or 2 examples. Okay, we want to convert a number 17.35, that's a decimal number. Obviously we want to convert into IEEE 754 32 bit single precision standard or single precision representation. So few steps are there. One, you have to convert the decimal into binary, we know that. Okay, the second step, quite important, that you have to convert that into the form 1.n 2 raised to e minus 127. This is the standard format of single precision number, that is a single digit 1. In binary 2 digits are there, so you have to make sure that there is 1 before the decimal point here. Then there is n, that is the fractional part, then 2 raised to e minus 127. So look here, step 2, our number is this 1.001.0101 base 2. Okay, so this can be written like this, which is equal to 1.0001001 into 2 raised to 4. So this is the scientific notation of the number. Okay, then here you have to find the value of e. So the standard format is 1 into n 2 raised to e minus 127 is equal to our data, that is 1 point something into 2 raised to 4. So you can see when you are matching all these things, n we have dot 0.0001001 here, e minus 127 is equal to 4 here. So what is the value of e, the exponent? Exponent is equal to 127 plus 4, 131. So this 127 is actually known as the bias. 127 is actually known as the bias. Here e minus 127, that is standard value, it will not change for any data, it is remaining as such, e minus 127. Okay, so you can calculate the value of e is equal to 131. So binary of e you have to find. What is the binary of e? 131. You will be getting the equivalent binary. Now you have to represent it. So look into the format. The first bit corresponds to the sign. Here it is a positive number, so 0. Then what is exponent? Instead of exponent, you have to write the value, the binary value of 131 here, because if you are looking, you can see the exponent as 4. No, it is not 4. You have to add bias to that, so that you have to keep the binary value of 131, which is equal to 1 0 0 0 0 0 1 1. That is the exponent. Then what is Mandisa? The data that is available after the decimal point. Here it is 0 0 0 1 0 1 0 1. Then still few bits are there. You have to pad these bits with zeros. So you have got a Mandisa, you have got an exponent, and there is a sign also. We will see one more example. The number is given, you have to convert into binary, you got the binary. Then normalize the number, you have to write in the standard format, so you got a number. Then what is the next step? You have to write into the single precision format, that is, find what is the value of E. Here the value of E becomes 137. Find the binary of E, that will be the column you have to fill. You have got a number 137, so you have to fill the exponent with the binary of 137. So it's a positive number, you have to write a 0 at the sign, then the exponent, and the Mandisa, the number you have obtained here, you have to write in the Mandisa. And if the 23 bits are not filled, you have to fill the numbers with the space with zeros. Okay. Then again another example you can see here, it is a very small number, nothing to do. You have to convert the same format. So you got a number with the 2 raised to minus 4 as the exponent. So you have to find what is the value of E. You can see the value of E becomes 123. Find the binary of E and fill the exponent column. The remaining parts after the decimal should be written in the Mandisa, and sign, there is a change. This is a yes, this is a positive number, so the sign is 0 itself. Okay, so we are converting the decimal 0.1 into the corresponding floating point in IEEE 754 standard. So it's a very small number, 0.1. Okay, it's a small number, but you can represent it very clearly by using the floating point format. So you can represent the number, a huge range of numbers can be represented by using IEEE 754 single precision format. Then in double precision, okay, the things are remaining as such only, except the number of bits. The first bit is for sign, then there is exponent. Here we are using 11 bits, and the precision is 1023. In the single precision it is 127, but here it is 1023, and the Mandisa 52 bits are there. So this is double precision. Double precision means the number is more accurate, it's more precise. That's why it is called double precision number. Even very small numbers, okay, can be represented by using double precision standard. So these are the questions for homework. What's represent the given examples of single precision to double precision, and represent the values already given in the examples, and what are the advantages of floating point. Okay, thank you.